over the last 3 or 4 years. I haven't been in New York actually for more than 5 years now. I mean, even though you guys are in New York, probably you stay at home most of the time. It's very nice to come back and give an in-person talk here, and without have to worry about a lot of these restrictions. I'm very happy to give this lecture in person, and also I'm happy to see quite a few people sign up on the Zooms. So today's talk is about searching. Got it. Today's talk is about searching for targets in the ocean. So as you may already know, searching for targets is very difficult in the ocean, and there are recent, not so recent, for the last 10 years, there are a few very high-profile cases of searching search that have to happen in a very harsh ocean environment, like this, Malaysia flight 370. The search took 5 years and still couldn't find the airplane, and also a little bit earlier than that, the search for the Air France flight 447, the black box, took about 3 years to find it. And earlier than that, in the 1960s, the U.S. Navy lost a submarine near the Strait of Gibraltar, and the nuclear submarine carries, not lost a submarine. The submarine lost a nuclear bomb near Gibraltar, and we really have to find a nuclear bomb, right? Recover it. So over the years, search has been a central topic, especially for the Coast Guard and for the U.S. Navy. So there are scientists and researchers who have developed very elegant theory guiding the search, especially in the ocean environment. And the U.S. Coast Guard has this operation manual telling them what is the standard procedure to do search and rescue whenever you got a fisherman get into trouble, and then they call the U.S. Coast Guard, and Coast Guard follow these procedures to search for this person. So from an academic point of view, there are these 2 books that are the must read if you care about this search problem. One is this Optimal Search Theory by Larry Stone, and also Search and Detection, by Alan Washburn. These are very well used textbooks when we teach students how to do search. So roughly speaking, there are 2 kinds of search strategies that are known to us. The first strategy aims to reduce the uncertainty of the target location. So if you have a target lost in the ocean, the first thing you want to do is to gather all the possible information and to try to pinpoint roughly where this target is, and try to focus your search power on the place where it is most likely to find this target. Okay, this is exactly what people did to search for the lost airplanes. The second strategy is if the target actually emits some kind of signals, then you could use your search platforms to actually detect the signals and try to move in the direction where you increase the strength of the signals, assuming like the closer you are to the target, the higher strength the signal is going to be, and then get closer to the target. Like in the early stages of searching for MH370, the assumption is the black box actually constantly emit a ping, and the assumption is that battery hasn't run out yet, so they will actually try to get that a few AUVs try to pinpoint these pings from the black box, and I remember when I was watching for the television about the search process, at a given day, one of the one of the AUVs actually detected a ping that very suspicious is coming from the black box, okay, but then it lost it. So it doesn't have that ping continuously, so it couldn't follow the gradient of the signal strength to reach the target. So basically, the first strategy called reduce uncertainty, right? Try your best to pinpoint the location where most likely you can find the target. The second strategy is follow the gradient of certain kind of signals so that you can find the target. Surprisingly, or maybe not so surprising, all the search strategies we know so far are one of these strategies or a combination of both. Okay, and now you can go home. All right, so what I'm going to talk about most, the next is, how can we engage marine robots to perform this search in higher efficiency and lower the cost of search. Okay, so also let's keep in mind that in the underwater environment, search is very difficult. Okay, why is it so difficult? Because first, the localization service in the ocean environment is more difficult. Okay, so under the water, you don't have electromagnetic wave, you don't have GPS signals. You only have GPS signals when the platform is on the sea surface. Okay, so underwater we have to rely on acoustic signals to do localization. So it's very difficult. And second, underwater, because we don't have cell phone signals, right? We have to use acoustic signals to communicate, right? To transmit information among the robotic platforms, right? And acoustic signal has much lower frequency than electromagnetic waves. So therefore, you cannot transmit a lot of information. Like if you download it right now, you can download videos on your cell phone, but underwater, transmit just one single image is very difficult. Okay, so we have this very severe constraints on communication performance, and also, I think everybody agree with me that swimming is harder than walking, right? You spend 15 minutes swimming, you consume much more energy than 15 minutes of walking, right? So the same thing for any robots to swim in the ocean. It will consume much more energy than, let's say, moving on the ground or even flying. Okay, so this is the three biggest constraints of performing underwater vehicle or marine robot operations. We really have to have these constraints in mind when we talk about different search strategies. And also, when we design our search strategies for marine robots, we want to borrow some wisdoms from marine animals. Here in this talk, we will borrow some wisdoms from little fish here. This is called a golden shiner. They live in swarms in waters. Okay, you see them quite often. And also crabs, right? This is a season where you can buy blue crabs in New York, I guess. Yeah, and here I put in a Kongsberg AUV here, which has very powerful computers on board and very powerful sensors on board. So the computing power of these three devices are comparable. Yeah. So any strategies that works for the marine robots, works for the animals, could be easily implemented on a robot, right? So it's not a problem of computing power. It's more like what is the strategy, right? Okay. When we talk about search, we can use a lot of different sensors to perform search, right? We can use sonar, right? We can use, if the water is clear, we can use camera, right? So over the years, to compare the performance of search strategies, people developed abstract models for the sensors. And this is very easy to understand. The first model is the cookie cutter model over here. Yeah. So this models the one-look detection rate. So basically, if you are within this range here, you are guaranteed certain probability of detection here, right? And the number, the probability number depends on how big this detection range is. And then we just assume like if you're out of this detection range, the probability drops immediately to 0. It's either 0 or it's either some probability detection. Okay, thank you. It's either some probability of detection or nothing, right? It's called the cookie cutter model. And then on the right-hand side, we have this, called inverse cube law. So pretty much it's better than the cookie cutter model, saying if you are very far away from where the target is, right, the probability detection drops as an inverse cubic of the distance. Yeah, I think we have a little animal that's flying here, yeah, and which projects its shadow onto our slides. We're talking about bio-inspired strategy, right? I mean, we're coming to that. Yeah. So these are the two most popular sensor models that's used to compare the performance strategy. All right. Then, in order to actually measure how good the overall search process is, we will introduce a few abstract concepts that combines the sensor models. And please bear with me. I know this is probably a difficult slide, but bear with me. First, we need to introduce the concept of a target distribution, which is a probability that the target is actually in cell J. We first discretize the entire search domain into different cells and index them, right? So let's say pi j is a probability that the target is in cell J, which we actually don't know. If we know the probability, then we can just search for the cell with the highest probability pi j is, right? The point is we actually don't know pi j before the search. And then we need to incorporate some kind of search history information to try to increase our chance to find the target. So then we have this detect gain distribution D. Okay, this D is a little bit abstract. Is DJI, it has two indexes. J is the cell J, and I is the number of looks you already performed in cell J. So pretty much this is what's saying that Dij is a probability of not being able to detect the target on the first I-1 looks, but in cell J, but successfully detect the target on the ith one, if the target is in cell J. Okay, why is this so? Because sometimes your sensor is not very good. So even though you stepped upon the target, you didn't know, there's a probability you're gonna miss it, right? You're gonna miss it. But if you keep stepping on the target enough times, right? Because the miss detection rate is finite. If you search it, the place in enough number of times, then eventually you're gonna find it, right? So this DJI is modeling that. And then the overall search performance is measured by this concept called probability of detection, which is a summation over all J, all cells, and over all looks, let's say the number of looks of the product of the two. The first is the probability for the target to be in cell J, and the second is, whether you're going to be successfully detect the target, right, for ith look. Okay, you sum over all of this. This gives you the performance of your search. Okay, so then good, we get all the tools that we need to measure how successful a search strategy is, right? So now let's look at some of the search strategies that's often used. So the first type of search strategy is also definitely the most well-adopted search strategy. It's called the long mover patterns. Okay, there are two types of long mover patterns are popular. On the left-hand side is the this zigzag pattern, right? It's called comb patterns. And the right-hand side is the spiraling patterns. You could be spiraling in or spiraling out. Okay, both patterns have been frequently used in reality, in the real search scenario. Okay, so if you think about these patterns, and also they're very easily to be implemented by an AUV, because all you need to do is to follow these paths. They're all straight lines, right? I mean, it's and with some turns, and it's very easy to follow it. if you think about these strategies, they give very predictable performance. I know by following these patterns, I can cover this entire area without any problem. Yeah, and I can predict how long the search will last, how long it took for me to be able to actually cover this entire area, right? They're very efficient. They're probably the fastest search strategy that one can have, okay, to cover the entire area, okay? However, there are a few, limitations of this strategy. The first limitation is it needs localization. In order to precisely follow these patterns, you need to know where the robot actually is, or where the search platform is, precisely. Right? Agree with me? Yeah. Yeah. Otherwise, how can you follow this pattern precisely? Yeah. And the second thing is, if there are some kind of obstacles that's blocking your sensor, sensor readings, blocking your sensor beams, which you don't know, then you're going to have blind spot that you're going to miss. There's certain area you're going to miss, right? Yeah. So you have obstacles, for example, in this grassland, and you try to mow around the obstacles just by simply following this pattern wouldn't work. Okay. So, and what is the performance of this strategy? Let's use our kind of theoretical framework to actually evaluate the performance of this. And you can see if you follow, if your sensor model is the cookie cutter model, yeah, and the performance increased almost linearly until it reached probability 1. Means you cover the entire area with probability 1, you're going to detect the target. Yeah, very easy to understand. If you use the inverse cubic law, yeah, the curve is not going to be completely linear, it's going to be curved. But then it's going to hit 1 also in finite time. So these two strategies are finite time strategies. That's why they're used frequently in real life searches. Okay. All right. These are man-made strategies, right? We invented them, we use them. But what are the strategies that animals will use, right? So these are some experiments performed by biologists by this group, Gautreau's group. And what they did is they put a bunch of fishes and they can mark the fish, right, and track the trajectory of fish in the tank. And the fish is searching for something, right? Obviously, they're swimming and searching for something. And the question is, what is the search pattern that these fish are using? Right? If you stare at it for about 10 seconds, right, can you tell what patterns are they using? Spiraling? What are some of your choices? Yeah. Well, the answer is there's no pattern. Right? The answer is actually they're performing a random search. All right, and their random search is not like the random walk model that the famous random walk model that we know of, right? And the little particles will move completely randomly. The fish actually keeps swimming forward. The randomness is on which direction they move. In other words, they keep swimming forward relative to themselves, but they change their direction in a random way. Okay, and this is modeled. Data was collected by Gautreau's group, and they actually identified a model called the persistent turning water model, PTW model, for swarm of fish. And there are more stories about how this PTW model works. But if you look at the first line of the equation, there is this random term telling you how the angle changes, the randomness of how random the angle changes is. And the sigma is a parameter that actually the bigger the sigma is, the more random the search is, the motion is, okay? And then this term, this is a desired steering, the changing rate of the angle, depends on whether there's obstacle in front of you, in front of the fish, how close you are to your neighbor. If you're very far away from your neighbor, you tend to swim towards the neighbor to form a swarm. So this is called attraction term. And also it depends on what's the moving direction of your neighbor? The schooling fish tend to align their movement with their neighbor. Okay, and here we're just doing some simulations of different parameters, selecting this KV and KP. KV regularize the alignment, KP regularize the distance to the neighbors. For the different performance, you get different trajectory. As you can see, like if you increase KP and KV, the two fishes here in the simulation become more and more similar. Their trajectory become more and more similar, right? If the KV and KP are small, then their trajectories becomes less correlated. Okay, yeah. So this is a well-established mathematical model trying to explain the behavior of the fish, the trajectory of the fish. All right, and this is definitely not one of the structured search strategies, right? So then the interesting question is, will this strategy work in terms of search? Yeah. Okay, so it turns out that this strategy, if you use our theoretical framework to evaluate this random search strategy, you notice that it will not reach probability 1 in finite time. It seems to, and in fact, the guess is like the probability just keep increasing until maybe it will hit a threshold. The question is, will this strategy guarantee eventually you will find the target, right? And it's very easy to guess. The answer must be yes. Otherwise, the fish species will die out, will be eliminated by nature, right? It has to guarantee that. So the question is, can we really show that as t goes to infinity, you wait long enough, the lifetime of the fish, you eventually going to find the target? Can we show that, right? And the technique we use to show that is a technique in stochastic system analysis and stochastic control is called the generalized cell mapping method. Is we actually first take the continuous time PDW model, we discretize it into discrete model, and then we're trying to convert this into a Markov chain process. In this case, we discretize the possible movement of a fish when they're in the center cell. We're trying to see, what are the probabilities for the fish to go to this 8 neighboring cells, assuming a 2-dimensional movement. For 3-dimensional, we have a different analysis, but very similar to this. You have more number of neighboring cells. And then from the data, we can identify a Markov chain transition matrix, probability transition matrix to model this random walk model, okay, of the fish using this Markov chain model. So this slide shows you a better illustration of this probability transition model. And these are the 8 different moving directions. And you have 8 directions here and 8 directions here. And let's say if your previous motion is in direction 2, what is the probability the motion is in direction 7? This is 0.02. Right? And here I want to emphasize that these numbers, like when I circle these numbers are extremely small. And these numbers corresponding to the probability that fish actually move backwards. They previously it's moved forward, and then the next move, what is the probability for it to move backward? The answer is 0. Okay, so the fish just keep moving forward, okay, from this probability model. But then the shaded areas are higher probability directions. Yeah, you can see the fish has the highest probability to keep moving in the previous direction, but significant probability of either moving slightly right or slightly left. Okay, by using these strategies, can we show that the fish will guarantee coverage of this workspace? And the answer is yes. And the technique we use is called reachability analysis with Markov chains. Yeah, so we convert this Markov chain transition model into a connected graph model, right? For this small motif, this nice cell motif, and then we actually, try to construct the connectivity of this entire workspace by dividing the entire workspace into this 9x9, 3x3 motifs, 9 cell motifs, and we're able to construct a graph that is fully connected, and which means that with probability 1. The fish is going to visit every cell okay, in this workspace. And also we are able to show that not only the fish will visit every cell, the fish will visit every cell from all possible directions with probability 1, if you let it run long enough. So it is obviously a winning strategy, okay, invented by the fish through natural selection, okay. And then with different type of random walk, if you compare fish random walk, it's different than some other type of random walks we know, like the original random walk and the correlated random walk, yeah. And you can see actually the fish random walk strategy is more efficient. In other words, it will cover more volume in a given time than other random walks. So why is that so? Because the fish doesn't go backwards. You know, why it doesn't go backward? Because the place you come from is the place you just searched. Okay, so by just doing this kind of locally greedy strategy, the fish is able to cover more space in a given time. It's very clever, right? And also we can use this model to analyze the search efficiency of a group of fish under different parameter selections. Okay, so this is a simulation comparing the search strategies of 10 fish under different value of sigma. As you can definitely see, like increasing the value of sigma definitely increase the search efficiency, right? It covers more area with higher randomness, right? And how to interpret this? You can think about the sigma as how hungry the fish is. If the fish is not very hungry, they tend to stay more together, less randomness. We stay more together, it's safer that way. Yeah, and we don't have to cover a bigger area in a given time. But if we get hungry, the fish get hungry, they just increase the sigma, increase the randomness in their motion, and they can cover a bigger area in a given amount of time. Of course, the risk is you're not going to be aligned as well with your neighbor as when you're not hungry. Okay, so yeah, I think we said enough about strategy 1, which is how you can reduce uncertainty, right? Increase the probability detection in a given time. So why not? Let's talk about strategy 2. Strategy 2 is in the case where you get some kind of signals from the source, right? And then you can use a group of robot or a single robot to actually estimate a spatial gradients that will lead you towards the source. And by following the negative or the gradient or the negative of the gradient, you are able to actually reach the source eventually. Okay, so this is the gradient climbing strategy. And also, in fact, here I just showed you that a robot can do this collective estimation of the spatial gradient by exchanging information with each other. You tell me what is your number, I tell you what is my number, and we can use a algorithm to calculate spatial gradient, and then we just move along the spatial gradient and we can reach the source. This is an engineering strategy. Fumin invented this strategy. It is, again, very efficient because following the gradient is the fastest, the gradient is the fastest, the fastest the direction that will lead you to the target, right? It's very efficient. It only requires limited localization because all we care about is our relative location instead of the global location. But it just requires limited localization. So these are good things. But the constraint is it requires frequent communication among the robots to share their measurements. As we just said, communication underwater is not easy, right? If you have a strategy that requires frequent communication, it may not be a problem for robots on land or flying robots, but it's going to be a big problem for underwater robots to do it. Okay, so then the question would be, can we learn from animals, about the strategy that doesn't require frequent communication, right? So again, we look at fish behaviors. So this experiment was done by Ian Cousin's group at then Princeton University, but now Ian is in the one of the Max Planck institutes in Germany. So the experiments he did was he put fish in this tank where he will create some light gradient here. On this side of the tank, the light is stronger. On this side, it's lower. On this side of the tank, the light is stronger. And fish like darkness. They like to stay in the shades. So he put fish in there. The fish will quickly go to this shaded areas. And then he did some numerical simulation based on the fish data, and you can see, like, suppose these red areas are the shade areas, then the swarm will very easily go and find these areas. Okay, and the nice thing is the fish does not talk to each other, right? Underwater, they see each other, right? But they don't talk to each other. There's this fish does not make sound. There are fishes that make sound, but this fish doesn't make sound, right? So what is the strategy they use? Okay, and here's the strategy. So before we talk about the fish strategy, let's talk about a very famous robotic model called Brandenburg vehicle model. So you have the Brandenburg vehicle has two wheels, left wheel and right wheel, and two light sensors, the left sensor and right sensors. The right sensor is connected to the left wheel, the left sensor is connected to the right wheel. Okay, and then the speed of the wheel depends on, it's directly proportional to the sensor reading. Okay, so now if there's a light source here, then this sensor will detect certain light intensity. The right sensor's light intensity is going to be smaller, or is being higher than the left sensor's light intensity, correct? Then the left wheel's speed is going to be higher than the right wheel speed. Then what's going to happen? The vehicle will start moving and will turn into the right. It will be turning to the right. And when it's turning to the right, it's going to align itself with the gradient of this light intensity. So it will turn until the left sensor and right sensor has the same readings, and it will just move directly towards the light by following that gradient. Okay, so it's a very nice gradient following strategy. Yeah. Okay, now let's look at how two fish might go to the source. All they need is like align themselves like these two wheels here, right? And then make their forward speed to be proportional to the sensor measurements they have. Right? In this case, it's like now the left sensor is corresponding to the right wheel and the right sensor corresponds to the left wheel. It's left sensor corresponds to the left wheel and right sensor connect to the left wheel. And if they do this, they will do the opposite of what this vehicle do. It will actually go to the shade, go to the dark areas, because it will turn away from the source, light source, and move away from it. Okay, so we call this speeding up, slowing down strategy because the speed of the individual fish is directly proportional to its sensor measurement, which is modeled by this one-line equation here. It's a very simple strategy. And all it does is to require the fish to be able to see each other and align with each other. They don't have to talk to each other. That's the key. Okay, and fish has great eyes. Okay, like even though the water is a little bit murky, but as long as they're kind of close to each other, they're able to see each other. Okay, so this is how this strategy works. And I'm not going to talk about more details about the theoretical analysis. Let's see how we can implement this using a pair of mobile robots. Think about each robot is a fish, right? They're not talking to each other. They're only, seeing each other. And every now and then they kind of randomly switch their direction. But then, this strategy also make them switch back. And then once they reach the light source here, yeah, and magic will happen because they random switch their direction and they will automatically get into this rotating pattern when they find the source. So it's a self-stopping strategy. It's very nice, right? Yeah. So, and how can we verify this on underwater vehicles? It's very hard to verify this on underwater vehicles. So we verified on a vehicle we invented called a flying underwater vehicle. This is a robotic blimp that has very similar dynamics as underwater vehicle, but it works in the lab and works in the air. Okay, and this blimp is very nice and it's very safe to human and it works for a long time. It's perfect for this kind of experiments. And here are two experiments we did using this SUSD strategy, using two blimps trying to go to the light source. Yeah, just like the mobile robot did. Now it's on the blimp. Okay. Yeah. As you can see, that this strategy actually lead the two blimps to the light source, right? All right. For the sake of time, I will skip this slides learning from the crabs. Okay, I'll skip the crab story. And now let's talk about how can we generalize this strategy to a larger swarm of fish, right? And in the larger swarm of fish, in the case of two fishes, right, it's very easy to align two fishes because you're my neighbor, I'm your neighbor. All we need to do is to see each other and align our movement. But for a large number of fish, this is a video again from Ian Kuhn's group. He actually marked how many fish that this fish here can see. So the red is the left field of view, the blue is the right field of view, right? You can see that the fish, it can see, there's a significant number of fish that a fish can see, right? Yeah, and also the interaction between the fishes are not constant. Yeah, sometimes it's random, right? So in this situation, how can all the fishes align their movement? Okay, yeah, so that's a question we're going to talk about next. And this alignment can be done through communication, right? Suppose you have a bunch of robots, each robot has a desired direction. All you need is to actually talk to each other and tell other robots where my direction is. And then the robots can run a protocol called Kuromoto model. Based on the Kuromoto model, they can run a consensus protocol. By running this equation, they can guarantee all the angles will align with each other. Difference between all the directions will converge to 0. Okay, so we already know that. Given communication, we can do it. Okay, in the 3-dimensional case, the Kuromoto model generalized to this more complicated dynamics. And each direction is now represented by a unit vector that lives on the sphere. And then the question is, how do you design this control U for each robot so that they will receive, assuming they receive the unit vector from their neighbors, how do they actually make sure its own vector is aligned with all the neighbors? Okay, and this is the average strategy. This is exactly the Kuromoto model we just see, but in a higher dimensional space. But as we just talked about, synchronization, this type of synchronization requires communication, right? The neighbors have to share their directions frequently. How can we do this without communication, right? And it turns out the solution is pretty straightforward. So suppose these are a bunch of data points here, right? Yeah. So let's just say each of the member here can compute something called the principal component analysis, which in a very hand-waving way, which can be understood as trying to find the longest axis and the shortest axis that can actually completely describe this swarm, right? And if for all of us, it's very easy for us to actually find these axes. For this swarm, the axis is like this one is like this, and this one is like this. So what are these directions? These directions are actually eigenvectors of this matrix. Okay, and this matrix is calculated by combining all the relative positions of these particles relative to the center. So you collect all the relative locations, relative vectors, and you construct a matrix for each one, and you sum all of the matrices up, and then you try to find all the eigenvalues and eigenvectors. Yeah, and then you pick the largest, the eigenvectors corresponding to the largest eigenvalue, which will be this axis, and then you pick the eigenvector corresponding to the smallest eigenvalue, which will be this short axis. And we can do this very fast. So does the animals. Okay, because you don't have to perform a eigenvalue MATLAB program in your brain to actually realize that these two axes are drawn this way, right? Everybody can do it without using MATLAB. Yeah. Okay. So, but the catch here is, if every component here, if every particle here is going to compute this axis, they automatically agree with each other. Right? Because when in this entire classroom, if everybody look at the same picture here, we will all compute the same vectors. We automatically will align with each other if we just compute the same vectors. Yeah. So to actually leverage this insight, we introduce a strategy based on the ALHA PCA flow, which actually just changed the averaged particle here by hitting your own vector with this matrix C, which is constructed from observing the relative positions from your neighbors. And then running this protocol, we can actually automatically compute the principal directions, which are eigenvectors of this matrix C. And using this strategy, if every fish is using the same strategy, then they automatically agree on the direction to move. And then by using SUSD, they will automatically align themselves. To convince you, I'm going to show you an experiment. Here, we're using the Georgia Tech Robotarium, which is an open access, robot testbed, which, every one of you can actually submit something to it, and the robot will run. And we just submit our algorithm to this Robotarium. As you can say, you can already see here, by adding in this PCA algorithms together with SUS strategy, we can have a swarm robot going to the source here, the simulated source here, without them talking. Okay. All right, and we talk about two strategies, right? Reducing uncertainty, gradient climbing. The question is, how can we combine the two strategies? Is there like a unified framework that automatically combine these two strategies together so that we don't have to worry about which strategy to use, and this strategy will just automatically blend the two strategies together, right? And for that, this is a PhD level work, which I'm gonna just briefly describe. Okay, so for that, we can introduce something called the Bayesian learning-based predictive control. Okay, so we actually treat this, robot locations as a state variable xk, and we assume the robot motion is very simple. It can be very complicated, but here let's stay with very simple. And we treat the target location as the theta, which is a parameter that we don't know. And suppose we have some kind of information and measurement, zk, and then we put in the posterior target distribution as pi k, the posterior detection gain distribution as SDK, which I already introduced before. And then we put in an objective function j as the function of all these variables, xk, uk, pi k, theta, and dk. Okay, and then under this framework, strategy one, reduce uncertainty, boils down to, given a measurement zk, we want to perform a Bayesian update of the target location probability, which is this pi k theta. Okay, and then we'll also update the detection gain because we performed one more search. So the detection gain update follow this equation. Okay. And then the second strategy, which is climbing the gradient, corresponding to, after I have done the update, I will find the robot motion, UK, to maximize my reward, my objective function. Okay, so this framework will blend the two strategies we just seen together seamlessly. So the first strategy is to perform Bayesian update. The second strategy is to climb gradient. And then how can we solve this problem, right? We can solve this problem by following a finite window receding horizon planning approach or modal predictive control approach. The idea is we set a, we set a planning horizon to be inverse proportionally to the entropy of the target localization. The entropy corresponding to how uncertain the target is. If the if pi is very uncertain, then I will put the planning horizon closer. But if I'm pretty certain where the target is, I can put my planning horizon much longer. Okay, and given the planning horizon, I'm trying to compute a bunch of actions during these planning window to maximize this cost function. And here I'm giving you this exact form of this cost function. The first term, remember, that's the probability detection. I want to maximize the probability detection. And the second term is the terminal cost. In other words, eventually I want to get as close as possible to the target. Okay, and also the first term, in the first term, this pi k corresponding to exploitation term, which is, you know, the best estimate based on the current based on the current information, the best estimate of the target location. But also on the other hand, I want to explore the environment a little bit. This exploration term dk, based on the previous search information, I want to, you know, explore the environment a little bit to make sure I understand the D a little bit better. Okay, so it looks pretty sophisticated, right? But it's a very nice framework that combines the two strategies together. And then we find out that actually this framework can explain a lot of the search strategies that previously invented by people or discovered by people. Like we have this 2007 Nature paper proposed something called infotaxis. You can view this strategy as, you know, ZK, the betterment is the number of detections, and then the J, the cost, is actually the reduction of the uncertainty and reduction of the entropy. And they wrote a pretty complicated task function here in that paper, yeah, and it's able to generate a trajectory of a robot that's actually going to the source. Okay, so this is you know, strategy previously invented by others, and then we you know, we can actually create a lot of different kind of strategies by combining the two using the framework. We can create, you know, infinite number of strategies by changing this J function. Okay, so for example, we can just change the J function by the expected number of detections of signals in a given cell, and you can see, you know, we can generate even better trajectories than the previous very complicated strategy, right? In exactly the same setting, right? But then all these strategies, they didn't take care of the probability detection, right? Their cost function does not include the probability detection. So what we did is, now what if we can just include the probability detection and then do this receding horizon or MPC approach to do target search, right? Here's a comparison. So the green line are the best one we showed before, that's called the expected rate algorithm. But the red one is the new algorithm we put in, is to put in the probability detection term in. As you can see that the red search, the red curve has a shorter length than the green curve in this scenario. And also in this scenario, in this same thing, the red search trajectory has shorter length than the green search strategy, which means the red strategy beats the green strategy by finding the target in a shorter time window. Okay, and also we are able to implement our strategy onto this little robot searching for this light field. Yeah, and this is one of the luckiest moment where the robot just moved and then find it. But then we did a lot more experiment from all those different initial conditions to verify this strategy, and I hope I can make you convinced that this strategy will work. Okay, and the next slide is going to, just for people who are about to graduate from a PhD program, is you know, in this blended strategy, there is a theoretical problem called the Bayesian consistency. Remember, the first strategy is we provide Bayesian updates of where the target is, right? We estimate the unknown parameter theta. The question is, as you move around, as you collect more information, is this computed probability of theta converts to the true probability distribution of theta? This is a very classical theoretical problem called the Bayesian consistency problem. In our situation, this consistency problem has not been previously solved. Okay, because the previous results requires the measurements collected are independent from each other. However, for the search problem, the measurement you collect are from the same target, and they are always correlated. So how can you prove Bayesian consistency in this correlated case? This is a problem we have solved And given these set of assumptions, which is much weaker than the independence of measurement assumption, we're able to show that our estimated target distribution will converge to the true target distribution, which is if you know the target, if beforehand you know the target is over there, with this strategy, you eventually will accurately know the target is at the location. Okay, you wouldn't search the wrong place. We can show this theoretically, and this involves some deeper math, deeper tools. For details, you can look at our paper. This is why I'm saying this is probably the paper you will appreciate when you are closer to graduation in your PhD program. All right, and so far we have developed a lot of theoretical work about search, but when can we actually use this in the ocean, right? And this has not been transferred to the Coast Guard, and the Coast Guard is not using these strategies, right? But how can we in the future transit more marine robots, right, into stakeholders so that they can use our strategy, they can use robots to help increase the efficiency of the search. I think in a university and academia environment, what we need to do is to develop more of these robots that can demonstrate the effectiveness of the strategies. And here, over the years in my lab, we developed some, really simple but easy to use robots, like the blimps, like the underwater robots, and the unmanned surface vehicles to actually verify our strategies. And one of the problems of performing research for marine robotics is it's hard, right? To get access to the ocean, it's very difficult, right? And here in this university, I know Professor Zhang always trying to go to the ocean, right? That's nearest place in the ocean to test these algorithms, right? But still, who are the graduate students, who are graduate students, Professor Zhang, you probably know how hard it is to get there, right? And how much time it takes to set things up, right? To do things. So that's why we're thinking that can we actually build open source, easy accessible test beds so that we can easily test underwater networking, underwater communication, right? Because underwater communication is very hard, very difficult, and also make the robots move around at the same time. So this vision actually lead Professor Zhang and me and a few other professors from other universities in University of Alabama and Michigan Technological University to actually get together to wrote a proposal to NSF and get it funded, so that the vision is to develop open source and accessible test beds for marine robots and also for underwater networking and communication. Okay, and one of the achievements we got so far is we now have this open source acoustic modem called BlueBus that you can download from GitHub right now. It's not like you can download the modem, you can download the design of the modem and build it. Okay, we have all the documents, all the part lists, and how to do it together. It's just like Arduino, right? And why we're building this open source acoustic modem, because if you want to go buy a pair of acoustic modem, it will easily cost you about $5,000 to $10,000, or even $20,000 nowadays. Okay, but if you use the parts here and you build your own modem, I think the total cost is about $250. Okay, so it's a big deal. It took us about 2 years to actually develop this modem, and right now we are vigorously testing it, but we already start sharing it, and it actually works. Okay, so you guys are welcome to, if you're interested in this, you guys are welcome to actually download this modem and get your hands on it and let us know what what do you think. Okay, and we're actually doing more than this. We're actually going to open source our mini robot that you just see on the previous page very soon. I want to end my talk here, and I want to thank all my sponsors from the Office of Naval Research and also from the NSF to support a lot of these activities that I showed today. And also, this work does not just from me. This is from my my group, which is pretty large, and over the years, okay, over the period of about 10 years, okay. But so there are a lot of details I skipped during my talk. So if you're interested in some of the things to know more about some of the things I talked today, feel free to contact me. Thank you very much.
Thank you. So next is the Q&A session. So any questions from the audience? Anything you're interested in? Is it easier to find things in space compared to water?
You mean the outer space?
Yeah.
I wouldn't see it's either, but I would say the challenges are different. Right. So like the communication challenges, like electromagnetic wave actually propagate pretty well in outer space, right? So the communication is probably easier. Localization, if you are not that far away from the Earth, then you have the GPS system for localization. So that might be easier. Okay, but the hard part is in outer space, you know, you could have like the temperature is going to be lower than in the ocean. Yeah, and also sometimes the temperature difference is huge, right? Like in, you know, if you are directly facing the sun, you could get really hot, and then when the sun disappeared, like on the moon, and then you get really cold. So these are some of the challenges in outer in the space robots. Yeah. Yeah. Radiation is also something will severely affect the performance of your electronic circuits. That's right, in space. Yeah.
Actually, last week we all talked about which Professor Archie from Ohio State, he's an expert in satellite communication in space. So he talked about that. He said many of the challenges are everything works in the lab, but when you send, you spend a lot of money and effort and send the product to space and so on. It's not working. That's really very frustrating.
Right.
And then
the frustrating part is the same between space robots and underwater robots. You always get frustrated, so that's guaranteed. So yeah.
Any other questions?
Yeah. Yes, they work for both. They work for both. And also at the end, I show this Bayesian learning based approach. And one of this, you know, the first step is we will estimate where the target is, right? And estimate that pi. If your target is moving, the estimation of the pi is going to be the same, but then you keep tracking. That's how you keep track the moving target. That is a very good question. Yeah. Your question?
You're using the atoms to use the localization, the name for the localization. But there is an actor when you have the battery of the robot.
Right.
Whenever the battery of the robot, we need to start to do the search again.
Yes.
Is there any to memorize the area that we?
Yes, you searched. Right. Yes. Wonderful question. Wonderful question. Yes. So the sacrifice you made by going to a random strategy, the gain is the localization, right? But the sacrifice, you definitely consume more power because the search process is going to last longer, right? So I would say, you know, in reality, you have to combine structured search together with this kind of random search, right? I'm not saying the random search is going to replace the structured search. However, if you think about the Bayesian learning-based search strategy there's a cost function you want to minimize or maximize, and you could put the power consumption in one of the terms, right? And then that will give you automatically would generate a optimal strategy for you, right? So that's why in the end, I want to introduce that framework, even though that framework has not been used in practice yet, right? But it probably represents the future, right? Yeah. Yeah.
search function to, so you can make a gradient of where you want to search on the surface. Then like how you could go to there.
Yes, yes. Everything I talk about today, you know, I illustrate everything in 2D, but everything works in 3D space. So yeah. So the algorithm, the theoretical work, everything works in 3D space. However, verify the search performance in 3D space is significantly harder than 2D space, right? Yeah. So this is why we probably need a better test bed, right? And so that we can just imagine if you have a lot of marine robots that you can easily use, like in your lab, or you know, you can just have a water tank and put a water tank and just like running this robot like raising a pet fish, and then you can easily verify a lot of things, right? That will completely change the game, the research of marine robotics. Right now, the problem of research in marine robotics, we need more people to how many people here work on marine robotics, right? I mean, right? Raise your hand. Raise your hand. You see, that's a problem, right? Yeah. So that's why we are trying to do this open access, open source research test bed. Yeah. Yeah.
So in the end, I think that testing so one
Right.
thing that the real life actually is the thing. And I mean that the started with top down, we kind of so
Right.
in real life how effective.
Right. Actually, for the blimp, we can verify some of that. We can use a fan to generate wind in the room, which you know, emulate the flows and waves. You know, we actually, I have another talk about that. You know, so yeah, so yeah, it just, if we keep working on it, we'll find very clever ideas to actually help you to validate things, right, in a harsher environment. Yeah.
Just follow up. So I mean, the machine learning is Bayesian. Implementation is a big aspect. So
right.
You're thinking about using some of the data collected for them improve the modeling more.
That's right. So here, the Bayesian learning-based network is just one type of machine learning tools here, right? We're using Bayesian learning, yeah, which is also a branch of machine learning. But I guess what you mean is, can we use deep learning, right? Because everybody wants to use deep learning. Yes, big time, because you know, I remember I abstracted the sensors into the cookie cutter and inverse cubic law model, right? Yeah, but actually, in real life, the sensors are much more complicated than that. And to process the data from those sensors, a lot of people are using the deep learning model, just like you process images right now. Yeah, so I have seen some amazing results on underwater sonar, like synthetic aperture sonars. You know, like they can really produce very high resolution, you know, acoustic image now about the target, just like a camera image. And for that, you really need deep learning. Yeah, definitely. Yeah.
I actually have one question.
Right.
Again, first of all, I'm not the expert in robotics or anything. So, but my background is computer networks.
Right.
So in computer networks, we have one type of fundamental networking problem. That's a routing problem. Final round. In the routing problems, when we design routing problems, one of the key factors is how to avoid a loop in the routing path.
Right.
So now back to the algorithm that you're talking about. We're trying to find the target, find the located object by searching the area.
Right.
So how do you prevent running into the same area time and time again?
Right.
You have to assume that you have an algorithm to make a certain decision at a certain point. So the next time you do that point, you make the same decision.
Right.
And then you follow the same track.
Sure. Yes. Wonderful question. Actually, the random search strategy do not try to avoid searching the same place more than once, right? Because if you think about the sensors as imperfect, to make sure you're going to find the target, you want to search it more than once to actually, to actually make sure you actually find it, right? So in reality, when people search, they always use a low resolution sensor first to scan an area, large area, because it's fast. And then they pinpoint suspicious areas, and then they send in high value, high resolution sensors in there to make sure. So that's the difference here. But then, if you formulate this into this Bayesian learning-based model predictive control framework, right? Actually, you can actually get a solution which give you probably the best number of looks that you're going to perform in a given region. Okay, so in other words, the optimal path will automatically consider the number of repeated search you need to perform there, assuming your sensor model is correct, right? So how can that big assumption? How do you make sure that assumption is not completely wrong? This is where deep learning, where these new tools that we invented in recent years can actually help. Okay.
Any other questions? I think we want to share the graphs.
Oh, the crap. Yeah. Okay. If you guys are not hungry enough, so let me share the crab story. Yes. I actually intentionally loaded. So the problem here, the challenge here is, when we are trying to climb gradients, sometimes the gradients is really hard to compute. If you think about this plume field, right? And the concentration of the plume is varying very fast over a space. There's a lot of high frequency noise, right? So if you want to use some numerical algorithms to calculate the gradient here, you got that noise. So there's almost no gradient to climb. How can animals handle this situation? Well, the crab is a champion of this. So the crabs has sensors at least here on the left clamp and right clamp, and also a sensor in the middle. Okay, so what they do is they can actually detect these plumes. Okay, but they don't use the strengths. Well, I shouldn't say this because my biology friends will kill me. But they compute the strengths, but also they compute the duration of the plume. So in other words, they do some kind of signal processing on board, and they calculate the duration of the plume, right? And the duration information is very, very important, because as you're getting closer to the source, the duration of the spikes, the plume spikes, is going to increase. So now if you use this derived signal, you're going to have a well-defined spatial gradient. Okay, and then we can just use that and use the same SUSD strategy. But in this case, our moving speed is going to be proportional to the plume strength instead of to the actual plume value. By using that information, we're still able to actually go to the source. We haven't done robot experiment on this because it's very difficult to generate plumes in the lab, and being able to measure it. So, at one time, I'm just joking today because everybody's relaxed. And one time I tried to work with a professor who actually build olfactory sensors that simulate the olfactory cells in dogs' nose, right? They call it electronic nose. And I was trying to get electronic nose to be installed on a vehicle. But I was not able to do it because it was too costly, and it was a prototype that doesn't work well. So I'm looking for good electronic noses. If you guys know a pair of electronic noses from Taobao or from from Amazon, let me know. Okay, yeah, and I'd like to buy a pair. So, yeah. Yeah.
Okay, I guess that's it. Okay, thank you everyone for coming.
Okay, thank you.
Okay, if you have a Zhang, sign up figure out the sign up. So,